Okay, so in this video, I'm gonna look at the two Higgs doublet model in Lean 4. So I might not do everything about it. We might not get very far, but I thought this would be, a good example of using Lean in physics. This is not scripted. I haven't prepared anything. So you're basically going to see me writing code for the first time, which is, of course, susceptible to difficulty and failure. Um, so bear in mind that when you're watching this video. So what is the two-Higgs doublet model? On the screen, I've got a paper that talks about the two-Higgs doublet model. And basically, it is a model, it's a model of a particle physics that involves an extra Higgs boson compared to the standard model. So for the standard model, the scalar potential is pretty simple. Whereas for the two-Higgs doublet model is much more complicated. And this is what you can see here. So this is the scalar potential of the two-Higgs doublet model. So what this means is that you have two fields, phi1 and phi2, and a field here is basically a map from space-time to the complex, to the a two-dimensional complex vector space. And this potential is a map that basically takes two fields, phi1 and phi2, corresponding to the two Higgs doublet model, the two Higgs doublets in this model, and gives you out a real number. And of course, this function is smooth. It is in fact invariant under a group action, the action of SE2 and SE3. And as physicists, we're interested in the minimum of this potential, because that is what happens when, when the Higgs boson, the way that the Higgs boson gives particles mass in physics is basically by sitting in the minimum of its potential, and something similar happens in this two-Higgs doublet model. So for this video, I'm basically going to try and define this potential. We'll see how far we get. And I'm going to do this in Lean. So if you don't know what Lean is this form of proof assistance, and my recent paper has been about using Lean in particle physics, using Lean in high energy physics, and the benefits that that can have. So we are basically going to encode or digitalize results relating to the two-Higgs doublet model in Lean. So the first thing we're going to do, and like I said, I'm working within HepLean here. So I'm working, Lean is the programming language, whereas HepLean is the library, or a library written in this programming language. So the first thing I want to do is, of course, create a file. So currently, HepLean has things related to anomaly cancellation, flavor physics, group theory, space-time, and the standard model. Like group theory and space-time are just standard results that you need to do all the other stuff. So let me first create a folder for beyond the standard model. And within that, let me create another folder for the two-Higgs doublet model, like that. And we shall make a file in this folder called basic. And that's basically going to contain, pun not intended, all of the definitions that we need. So the first thing we want to do in this Lean file is the copyright. That's because otherwise the linters, which check if the code is formatted correctly, will complain at us. Yeah, and then we want to make a namespace. We want to make a namespace. So let's make a namespace. Let's call it two-Higgs doublet model. Will it let us do that? No, it won't, probably because it's a 2. So let me call it two-Higgs doublet model. Like that. Okay, so this namespace basically means that any definition or any theorem that we name will have 2HDM as a prefix to that name. So it helps with like naming things twice, the same thing. If they're in different namespaces, that's okay. Notice that I'm using GitHub Copilot here. So if it looks like I've written something really quickly, it probably means that GitHub Copilot has written in it, and I pressed tab. So you'll often see this faint words appear on the screen. Let me actually zoom in a bit. like that. You'll often see these faint words on the screen, and that is GitHub Copilot trying to prove something, trying to state a theorem. So let's see what we've got. So the first thing we want to do to define the 2 Higgs doublet model is to define the fields, phi1 and phi2. So luckily for us, HepLean has already done, there's already stuff about the Higgs boson in HepLean. So we come over here and we look at, will it be? It'll be in the standard model, Higgs boson. And we go to basic, we'll find there's already a definition of a Higgs field, and it's defined as a smooth section of the Higgs bundle. The Higgs bundle, if we go up here, well, we can actually, let's see if we can just press Command and click on that, and that will take us to the definition. So the Higgs bundle is just the trivial bundle of space-time across the Higgs vector space, and the Higgs vector space is a Euclidean space, Euclidean two-dimensional space. It's basically a two-dimensional vector space. Ignore the fact there's Euclidean here. So what a smooth section of this bundle is a map from space-time to the two-dimensional vector space. And this is what I said here. This is what this definition of phi1 and phi2 is. So what we can do is we can come over here and we can just import that definition. So we don't have to define it again. And to be honest, defining it again would be bad because, that's work done twice. And it means it's harder to be consistent between the two places. So let me try and import this. Standard model. Higgs boson basic. Okay, perfect. So now we should have access to phi1 and phi2. So, sorry, now we should have access to the definition of a Higgs field. So phi1 and phi2 here are basically a Higgs field, and we want to define a potential. So let me start by actually just writing potential. Phi1, phi2. And what we're going to assume they are Higgs fields, like this. And what do we want out of it? We want a real number. So notice that to do this I press \R in a space. And let's just put sorry for now, because we have to work a bit to write down this definition. Okay, so let's see what we have. Let's start with this term here, this M. Well, actually, before we do that, let's look at the Higgs boson and let's look at its potential, because the Higgs boson potential is already in HepLean, so we can basically copy what has been written there. Okay, so for the Higgs boson, the potential, sorry, for the Higgs field, the potential is defined as using this norm squared thing. Okay, and norm squared is defined here as it takes a Higgs field and it goes from space-time to R to give us, basically taking the norm of the vector space in Euclidean space. And that's why this definition of the Higgs field of the Higgs vector space is Euclidean space, so that we can define that Euclidean norm. So the first thing we can do then is pretty simple. So the first thing we want to do is we want to write down this term. Then we need to define M12. So M12 is actually a real number in this potential. So let's define M12. And this squared, this number a priori doesn't have to be positive, even though there's a squared there. So I'm going to define A12 squared to be a real number. And let me get rid of the by for now. we can define the first term of our potential. So this term here, this M, oh, actually that should be a 1. This M11 term as M11 squared times by 1 times by squared norm. That didn't work. Norm squared. Why did that not like it? Invalid field notation. Let me come down here and see. She needs to be here. So norm squared. It is norm squared. Higgs field. And then it's a Higgs field. So, okay, I think, let's see if this is recognized as type. It has not. Let me remove it. It has not. So what I need to do, and the reason this hasn't worked, is that I need to open here. What do I need to open? I need to open the standard model. So open is different from namespace. Open is basically saying we're going to use the results from this, and we don't want to, have to prefix that with standard model. So let's check. No, Higgs field is still undefined. Let's remove it. Okay, that's good. So that's now recognizing Higgs field as a type, and it's saying a Higgs field is a smooth section of a Higgs bundle. Good. So what it's questioning now is that there is no in HepLean there's no definition of times in a real number by a field. So the problem here, and I should have noticed this coming, is that this potential is a function of space-time. So we need to put X here, and X is a member of space-time. Let's see if that worked. It did. So we can put X there, and that should work. And that is going to tell us that this, something throws an error, compiler, non-declaration, unknown declaration. Why is that complaining? It is possible that this is not compiled. Let's go up. So what compiled basically means is that the compiler can read it. It looks like it should be. Let's see if I have anything that's non. Okay, yes. So apparently this is all non-computable. So let's put this in a non-computable section, and that should get rid of this error. Okay. So that's the first term. Good, we're making progress. That's the first term in this Higgs potential. So this is term number 1. Now let's do term number 2, which is this term here. So term number 2 says it's basically the same. So what do we need? We need M22 squared, and that's a real number. And then we want to add this. So let me do my indentations correctly. We want to add this to M22 squared minus by that. Good. Okay. And now we want to do this term. So this is like the cross, the mixing, the mass mixing term between the two Higgs potentials. And it's here that M12 is potentially complex. So we need a notion of multiplying two complex numbers together to give us a real number. Sorry, two vector spaces together, two Higgs fields together. And this is actually a complex number. And then when you take the conjugate, you get back a real number when you add the Hermitian conjugate. So let's see what we can do here. So let's go back to our standard model definition. And our standard model definition does not have the notion of multiplying two Higgs fields together. So what we can do is we can define this. Let me define it here. Let me define the inner product of two Higgs fields, phi1 and phi2. And what is this going to be? This is a map from space-time to R. And then GitHub Copilot tries to complete it for us. R there. Good. Okay, so that is the definition of an inner product. And let me give it a documentation. Okay, so it's basically you take the two Higgs vectors, you evaluate them at a point, the point that the space-time point, and you take the inner product in the Euclidean complex numbers. Sorry. Ooh, okay. You should be able to take actually this should give us a map to the complex numbers. There we go. Okay, so this is a map to the complex numbers. And it's given by taking their complex inner product. Good. Okay. So the thing that we have to check to make sure this is okay is how that inner product is defined. I'm slightly worried it is defined as the dot product without complex conjugation, and we want complex conjugation here. So we can test that. Let's see how we can test that. How can we test whether this is how this is defined? Let's see. Okay, I don't want to define these to be smooth. What I want to show is that if it was defined by a complex number, then it would be true that this number here is equal to the conjugate of this number here. Okay, so let's see if we can prove this in any easy way. And we can. Good. Okay, that's good. So that means our definition is the correct one. Perfect. So we can come back over here. We have to restart our file. And we should be able to write down our second term, which is this here. So what do we want? We want a M12 squared, and that's going to be a complex number. And our term is going to be, let me bring this back over here. So it's minus M12 squared by 1 dagger phi 2 plus its Hermitian conjugate, its complex conjugate. So let's go minus M12 squared times by phi 1 dot inner product by 2, and then we need to multiply u by x. And the problem this is now complaining at is that this number is a complex number, whilst this number is a real number. So the basically the way that we want to do it is the way that it's suggesting here, that the GitHub Copilot is suggesting. So the error that we have now is that it doesn't know what conj is, so we need to open complex. I actually think we have to open complex.conjugate. Okay, open complex conjugate. Like that. List. Okay, this X is in the wrong place. Let's put X there. Actually, X is still in the wrong place. Put X there. And phi 1, phi 2. And hopefully that should be okay, but it's not. So why does it not like this? Because GitHub Copilot is trying to be, well, actually, I put the brackets around. Me trying to blame my AI for my problems. Good. So this now looks correct. Let's get rid of these brackets that I put in. Can I even get rid of these ones? Excellent. So this real here isn't like you don't need that. Technically, this number is a real number already. I mean, it's a number plus its conjugate, complex conjugate. So this number is real. The reason you have this real is because otherwise Lean doesn't know that this is, it still thinks it's a complex number because, you know, we haven't told it that adding two complex numbers, adding its conjugate to itself is a real number. But it's something we can check actually, and this is probably a good thing to check to see if we can do this. So let's go over to Google, which is basically the search engine, and let's see, what should we type? Real and complex, and see what we get. And conjugate. Okay, let me see if I type that in. Complex conjugate of real. So that's a theorem that the conjugate is the same. Let's see if I put add. Okay, so I don't see anything manifest. Okay, but that's okay. This real is not so bad. Okay, so the second term, let me come back over here. Let me. So we've got this term, we've got term number one, we've got term number two, we've got term number three. Let's go for term number four. So this should be fairly easy. It's basically half times by the norm squared. Actually, term number one, sorry, term number 4, 5, and 6, or and 7, well, 7 is slightly more complicated, but term 4, 5, and 6 and 7 are they look somewhat easy, and then this is slightly more complicated. So let's write those terms down. Okay, so what do we want? We want lambda 1. Lambda 1 is for a real number. Why do you not like that? You do not like that because you don't like the character lambda. Which is annoying, and I think there is a way around it. And I think I have used this when I wrote the code for the one, um, the one, the normal Higgs boson, and it is this. Okay, so will you let me do this, or are you gonna complain? You are gonna complain. Okay, let me not do this. Let me instead of using lambda, let me use our um uh let me use lam. Let's call it lam1, and then we can rename it later. So we want lam2, lam3, lam1, lam2, and lam3. So these are all real numbers. And the term that we want to write down, let me just put it on the screen. By the way, if you want to open this paper, it is this is the archive number. So yeah, we want to write down this term here, and then this term, and then this term. Okay, so what do we have? It is 1/2. Good. GitHub Copilot does that for us. I can just press tab, and that is, let me just double check. That is exactly what we want. Plus lambda 3, and lambda 3 is exactly that. And the term lambda 4 is this term here. So it's kind of like this inner product times by this inner product. And there's no half. It doesn't carry a half. So 4 times by, good. Let me put X there, let me put X there. And let me put real, because Lean doesn't know that's a real number. Although I could, if I wanted to, actually define this as norm, which I am going to. Good. Okay. So, and then we're on to this last term, this term in brackets, which is 1/2 lambda 5 by 1 by 2 squared plus all of this stuff, plus this Hermitian conjugate. So let's first of all define lambda 5, lambda 6, and lambda 7. Let me get rid of the b to be consistent. And lambda 5 is 1/2 times by lambda 5 times by, what is it? It is, I'll show you, it is this quantity squared. So it is this here squared. Not normed, but squared. And then we add its Hermitian conjugate. So let me put a bracket around all of this. And its Hermitian conjugate of that, and we swap 2 and 1 here, and then we put RE there. Okay, and then lambda 6, lambda 7 are phi 1 times by phi 1 phi 2, and phi 2 times by phi 1 phi 2. So let me go plus lambda 6 times by phi 1 dot norm squared x times by that. And let's plus its conjugate, which is not quite what GitHub Copilot wants, but very similar. We can just put the RE to tell Lean that is actually a real number. And then the final term is exactly what GitHub Copilot wants us to write. And there we go. That is the potential of the 2x doublet model. So this is the LaTeX version, let's say. And then this is the Lean version. Yeah. So what we can do is we can give it a doc string, so we put the potential of the 2x by the 2x doublet model. And that's good. Okay, so I'm going to stop this video now. But if I get a chance, I'll put one on about, showing that this potential has sort of the properties that we want it to have. For example, it is smooth with respect to x. I mean, here it is literally a map from space-time to R once you fixed all of the parameters. And yeah, to show it's smooth with respect to X is, of course, important. But it is important because in high-energy physics, you want to integrate over this potential. And to integrate, you need it to be smooth. So, perfect. Okay. Actually, maybe you don't need it to be smooth to integrate. To differentiate, you definitely need it to be smooth. We also want to differentiate. But okay, good. So, yeah, hopefully you've taken something away from that. Yeah. Okay, thank you for watching. And let me stop the recording.